test on two different populations. I want to spend a little bit of time just going over a few more examples, and then we'll call it a day, and we'll move on to our last chapter, which is chapter 9, linear regression. So essentially in these stories, there are going to be two populations, and we're trying to decide, is there evidence to prove that the first population's mean is bigger than the second, less than the second, or just different at some given significance level alpha. And we made up some examples, so I'm just going to find one here. So this is a version from your homework. Quite a few of these questions don't have the salt button. And it's okay that they don't have the salt button. All you need to do is go to some other question that does have the salt button, and you can hit that one, right? So it's not that you can do without it. So in question 6, the highway department is testing two different types of reflective paint for concrete bridge end pillars. So I guess they're trying to make them visible so trucks and cars are aware of them and don't crash into them. The two kinds of paints are alike in every respect, except that one of them is orange and the other is yellow. Okay. The orange paint is applied to 12 bridges, and the yellow paint is also applied to 12 bridges. Okay, so number 1 is going to be the ones that were painted orange. And population 2 then is going to be the ones that were done yellow. I got that. And it was applied to 12 bridges that were orange, and also 12 bridges that were yellow. That's fine. After a period of 1 year, reflectometer readings were made of these bridge players. I guess this is a machine that you point at something and a big number means it's more visible, right? So they're just saying, I guess, how quickly they deteriorate, right? So they're trying to find is orange, it's going to last longer, right? Be more noticeable longer, right? That's, I guess, what they're doing. And they have this funny machine called a reflectometer, and it basically gives you a number. I can imagine it's a little gun and you point it and it says 18 or something, you know, and big is better, right? If it says 2, you totally see the thing that's like, you know, vague grey. And in this case, the average reading that they got was 9.4, and that the standard deviation was 2.5. When they did the same thing to the yellow one, I think there's quite a noticeable decrease, right? That's not as good, right? It's deteriorating. And the standard deviation, they told me, was 2.1. And we're going to be using a 1% significance level. So they told me that. So that's basically everything that I got from the story as I read it. And we are going to then go through some of these questions. And I'm just going to write them down. The first one is, what are we testing in this problem? And the answer you're going to pick is, we're testing the difference in the means. And then the next question they ask you is, what is the significance level? And that's almost a stupid question because they just told you. You just read it and write it down again. Then they tell us to write down the null and the alternate hypothesis. And they give you a number of choices. So I'm just going to write down the one that's the right one, and you would pick that one from the list. Now, mu1 take away mu2 equals 0 is how we should standardize that. But for WebAssign, they write it down like that. But we talked about this yesterday. Aren't they exactly the same mathematically, right? There's no difference between those two. Now, in this story, and I should read a little bit more because I forgot to do that, based on this data, can we conclude that yellow paint is less visible? So we're being asked to prove that this is less visible. So we're trying to find that the difference between these two, is it greater than 0, is it less than 0, or is it just not equal to 0? Well, if this is less visible, doesn't that mean that this is bigger than that? So we would write it down in that format, right? But if you were doing it the way WebAssign is expecting it, you could say that, or I guess you could also say this. Oops, put that the wrong way around. That way, or that way. That's what was having in my brain. Right, first one's bigger than the second, or the second one's less than the first. Same effect. And then the next question it asks us, and you're going to pick the student T distribution. And the reason why we're choosing that is small samples don't know anything about its shape. That's enough to make it a T distribution, which every one of these is. And then the rest is they're wanting you to find the test statistic, and then the p-value, and then the conclusion. Now that stuff all is going to happen inside SALT. So I'm going to nip over and, oh, please work. Okay, got it. And that particular question, number 6, didn't have its own individual button, but all I did is I found a question that did have a SALT button and I pressed that one. So we are going to look at a 2-sample distribution. The first one was the data with the orange, so that had a number 9.4. It had a standard deviation of 2.5, and it was a sample of 12 ridges. And then the second one was the yellow paint, and the yellow paint had a 7.1 visibility score after a year. It had a 2.1 sample, and there was 12 of those. And the hypothesis test is that guy, and we are trying to prove that it's the first guy is greater than the second guy. And then we have that annoying decision to make, which I think they should make life easier. Do you think these two numbers are close enough that I should assume equal variance? Or do you think that they're not close enough, in which case I will not assume equal variance? And that's a kind of hit and miss sometimes, isn't it? So judgment call. Aidan, gut feeling, that's all you can go by. Are you going to say that these are close enough to be equal, or are they far enough away to not be equal?
They're far enough away to not be equal.
Then that's what you would pick. And now you would do generate results. And the test statistic is that number there. You see the 2.440281 thing? Right, that's called the test statistic. So that's 2.44 to 2 decimal places. Underneath it is the p-value, which is 0.0117 to 4 decimal places. And now I will return back to what our work would look like. So we would do test statistic, p-value. Right, now they normally finish with questions to do with, oops, hit the wrong button there. I'm trying to find, there we go. You then finish with things like, what's your conclusion, right? Well, that's where we would do this. Is our p-value less than significance level alpha? Is our 0.0117 less than 0.01? And in this case, I would say no. Agreed? And I'm not sure I'm in the right place. Let me make sure. There we go. So test statistic, that's the T guy. P-value. Is our p-value less than significance level alpha? The answer is no. And when it's a no, we will choose the sentence that looks like this. At the alpha equals 0.01, in this case, level. Oh, this is wrong. And not because Aidan did anything really wrong, but Aidan made a executive decision that they weren't going to be equal. Remember, I just said gut feeling. Nothing wrong with your gut feeling, but evidently it was wrong. I have no justification why they chose it, but they chose it to be equal variance. And because they chose it to be equal variance, it means that the answer wasn't the same as the one we wanted. So let's just, well, let me just check that. Yeah. So they said in their calculation that there was an equal variance. So I'm going to go back and show you the difference. I really wish WebAssign would make it obvious when you should do it and when you should have equal variance and not, but there's no way that I can see that they're doing it. So I'm just putting in the data again, and I'm going to put in one change. So this guy is 9.4. This is still 2.5 as it was before, and this is still 12. Nothing's going to change here either. The other group was 7.1. The standard deviation was 2.1, and that the sample size was 12. And we went down here and we put a 0, and we wanted to show it was greater than. And now I'm going to hit assume equal variance and generate the results. And now I'm going to generate the results again. There's virtually no difference in those two numbers. Would you agree? 0.115 and 0.117 makes no difference to the conclusion. So I must have been looking at the wrong place, which means I take it back. Aidan, your choice was fine. So we should be choosing at the 0.01 level. We fail to reject the null hypothesis. And we have, I think, an extra piece goes on the tail of that. And conclude that the data is inconclusive. Now, if that number had been, I know it's not, but if that number had been, say, 0.05, or if it had been 0.10, wouldn't the answer have been yes? And we would have said a different sentence, right? We would have said at this level, 0.1, we reject the null hypothesis and conclude that the data is significant. Yeah, wish I didn't have that little hiccup, but I think it's probably because I had to scroll up and down to find a salt button, that somewhere in that process I went and changed the numbers for the question, which it does because it's a pain in the butt. So you got a story, you know all the data about population 1, you know all the data about population 2, You're trying to prove something greater than, less than, or not equal to, and then you go into salt, put in your numbers. Eventually you will get a p-value. In this case, that one. And then you'll check your p-value. Is it less than whatever the significance level happens to be in this question? If the answer is no, you do a sentence that looks like this. If the answer to the question is the p-value less than alpha, if the answer is yes, then you do an altered version of this. So an altered version would be that you reject the null hypothesis and conclude that the data is significant. Are we good with that one? We follow the process. Okay, let's choose one that is a version of question 8. And a comparison is made between two bus lines to determine if the arrival times of the regular buses from Denver to Durango are off schedule by the same amount of time. Evidently, they're always off schedule then. For 51 randomly selected runs, bus A was observed to be off schedule on average of 53 minutes. God in Himmel. So basically, if you were taking this bus from Denver to Durango, couldn't you end up waiting an hour for it to turn up because it's late? 53 minutes on average. I do not want to get a bus with that kind of schedule, but evidently buses are not good at that. The standard deviation is horrible. Well, maybe it's not their fault. You know, traffic jams and congestion, you can't really predict what they're always going to be. And for this one, the random sample was 51 buses. And then over here, the second bus, there was 60 of them. And they had an average of 61 minutes. So they're even more inconsistent. And there you go. And the significance level that we're being asked to choose is the 5% one, which is that one. Look at what the null and the alternate would look like, and the way that WebAssign would write them. So you would start by just making them equal to each other, which is always the case. And we are being asked, is there evidence to prove, let's see how they phrase it. Does the data indicate a significant difference in averages? So they're just saying, are they different? So the alternate is that they're not equal to. Okay. So at this point, I'm going to go in and use salt, and we'll find the test statistic. And the p-value. So let's find that salt button again. Gotcha. And I'll zoom over and we'll go through the steps. First thing you're going to do is make sure that it is a 2-sample T. Bus line, the first one, has a mean of 53 minutes being late, standard deviation of 17, and there were 51 buses that they used to get that data. The second route, route B, is 61 minutes on average late. The standard deviation was 15, and on that bus route, they used 60 buses. Keep this as 0. Not equal to. I'm going to make an executive decision here, and I'm saying that these are different enough. Right, so I'm going to just leave it blank. And I think that would be my go-to thing. Now, if one of them's 8.2 and the other's 8.3, then I would probably assume equal variance, right? But unless it's obvious, I'm not going to attempt it. So I'm going to generate results. And the t statistic that we got is negative 2.61 to 2 decimal places. And the p-value, which is more important, is 0.0105 and some stuff. Those are the two key numbers that we would be interested in. Right, now that I've written it like this, I can now go on to the test, because that's where the conclusion is going to come from. Is the p-value less than alpha? Is this guy less than that guy? And the answer is yes. So we would do a sentence that would look something like this. At the alpha equals 0.05 level, we reject the null hypothesis and conclude that the data is statistically significant. And then the second sentence would be, we've essentially shown that there is evidence to prove that these have different averages. I think looking, would you agree, B seems to be much worse, right? Longer wait times than this one. Any questions about that process? Do you get a feel it's kind of collect the data, set up the thing, salt finishes it off, and then you're going to have a little conclusion, a yes or a no at the end. If it's a no, you do this sentence. If it's a yes, you do the one where you reject. So you rub out those words. You reject the null, and you conclude that the data is statistically significant. Try to see if I have any other questions I need to do. Do you want me to do one more of these, or do you feel you're comfortable with the process? We good? Right, great. So we are finished hypothesis testing, which typically is what most people would say was the hardest thing. I don't think it's particularly hard, but I'm not. I think other things are hard, but evidently for some people, that is it. So we are on our last chapter now. So we're actually ahead of the game, which is good. And we are going to look at chapter 9, which is scatter plots and correlation. We're going to go through a lot of theory today, and then we'll look at some questions from the homework after that. So, a lot of notes. So if you don't like writing notes, you can listen, and maybe you could go back and watch this video, pause it, and write down what you think is relevant for you. So first thing we're going to look at is what's called a scatter plot, because we're going to analyze data that consists of two variables. Very often, one variable is called the explanatory variable, and the second one's called the response variable. So I want you to imagine that we collected data, and we'll be collecting the age of a male and the age of a female. And this is the age at which they got married. So we're talking about married couples consisting of one male and one female in this data set. And the age of the male goes here and the age of the female goes here. So you can imagine that some people get married at 19 and 20 and 21, 2, 3. Oh, and it's the age of first marriage, right? 25, 26, 27, 20, and so on. So let's make it simple. Starting at 20, there's 30, there's 40, there's 50, there's 60. You know, some people just don't get married till they're late on in life. That happens. There's 20, 40, 60. Yeah. And so you collect data on married couples, and you find out what the guy's age is, and what the woman's age is. So for instance, you might have, he is 19 and she is 21, right? That's what that would look like. Essentially a coordinate. And if that was the case, wouldn't I plot a dot about there? And that's called a scatter plot. Right. And you might have, his age was 25 and she was 23. So that would be 25 and 23, might be. There. Now, can you imagine that you collected lots of data? You might not be too surprised to find that the data has a shape to it. And the shape I'm talking about is basically, isn't it mostly a straight line? But it's not a perfect straight line. You agree that there's lots of ziggy zaggies, some are big, some are small, right? But it's a kind of sausage, right? And that is a very common shape. So let's give you some names. The x-axis is called the explanatory variable. And the y-axis, well, that's going to be called the response variable. So if you hear a question talking about the explanatory variable, they're talking about the ages of the male. And if they're talking about the response variable in this story, now they could switch places, right? You could decide to plot the age of the woman against the age of the man, and that would be totally fine. But that's what we mean. Explanatory is the x and response variable is the y. And so these scatter plots, and I guess I should put a little heading here, age of their first marriage. You can see quite a lot in that data, and we're going to analyze what these scatter plots look like and introduce a vocabulary, like words, that allow us to describe something that's quite visual. So here are some scatter plots. And we're going to look at positive and negative. Positive and negative. And they stick a word next to it. Don't get me frightened by it. This scatter plot has a positive correlation. And this one, we say that it has a negative correlation. The way I typically see this is, if you're going uphill, it's positive, and if you're going downhill, it's negative. That makes sense as a name. Right? Positive correlation, negative correlation. Now, data does not need to be straight lines. This data set is also considered to have a positive correlation. Would you agree you're still going uphill? That makes sense? To me, uphill means as the x gets bigger, doesn't the y get bigger? Right? So in this case, it would look a bit like that. And of course, you can have negative correlation where you go downhill. So if I was talking about this scatter plot, wouldn't I say it had positive correlation? Would that phrase say, as the age of the male gets bigger, so does the age of the female, right? Curves all the way. So far, so good. First term, positive and negative correlation. Next term we're going to look at can happen in any one of these four shapes, and that is your scatter plot doesn't have to have them, but it might have outliers. Now we know what outliers are like, right? We've seen situations when you had a single variable, right? A lot of ages, but somebody was exceptionally old. So what would an outlier look like in a scatter plot? Well, I'm going to pick one of these guys again. I'm going to pick a scatter plot that looks like that, right? Would you agree this has got negative correlation? I don't think this is a surprise. Wouldn't both those be considered outliers? An outlier is essentially any point in 2D space which is distinctly different from the main shape. I tend to make them into sausages. And what I mean by that is I tend to imagine a sausage covering the data. And if you're outside the sausage, you're an outlier. Does that make sense? As a kind of visual way of thinking about it, right? Now, those are pretty clearly outliers. Let me show you another outlier, which some people find a little bit harder to get their head around. Now, would you agree that's positive correlation? That's an outlier. Now, why some people, I think, it's me putting words in their mouth, right? Why some people find that hard to believe that's an outlier is their brain sees a straight line and that dot looks like it's on the same straight line as all the other data. But isn't there a distinct gap? If you were drawing my sausage idea, won't your sausage stop there? Right. So outliers are any point that is distinctly different from the rest of the data. So as is that concept kind of clear in your brain? Are you comfortable? If I look at a scatter plot, I can tell if it's an obvious outlier at least. Great. Are we good? Right. Now, you shouldn't get a question that makes your life hard. But I mean, in reality, this is going to be something that you might have to deal with in your own data. Right, we all agree these two are outliers. Great. So I'm now going to put a green dot, another point. Is that guy an outlier? The one I just put in, I'm going to put a little number 1 beside him. Is number 1 an outlier in your brain? Because this is a judgment call right now. Does number 1 count as an outlier? Okay.
Yes.
How about number 2? And I wish I didn't have my sausage round it. Can you imagine my sausage wasn't there, right? Would you agree number 2 is darn close to the rest of the data, and that's definitely a grey area, if nothing else. If I did a dot there, that's number 3. Would that convince you that's probably not an outlier? Would you agree if I made my sausage a little bit bigger, that would fit totally fine inside it? So outliers are distinctly different, right? Clearly different from the rest of the data. And hopefully you won't get a question where, yeah, I'm not so sure now, right? So positive and negative outliers. Let's introduce some more vocabulary. And we're going to talk about the strength of a correlation. So think of correlation just a name for the curve, the scatter plot. Right? So spend forever drawing these little dot things, right? There we go. Some of my dots look like lines. Can you pretend that they're just dots and I made kind of... Here are 3 scatter plots. Each one is meant to be a negative correlation, right? You see it pointing downwards, negative. My sausage does help me here. Would you agree that all these points are pretty close together? We would say that had strong correlation. So far, so good. I'm just closing some windows here because I want to go back in and open some up in a second. This one, we will use the word moderate. And this final one, we're going to call it weak. So, moderate and weak. If you think of the sausage concept, aren't strong correlations skinny sausages? Aren't moderate kind of fattish sausages? And lastly, aren't weak correlations almost not like a sausage at all? Aren't they almost like a big circle, right? So if the data is close to each other, it's strong. If it's a little bit further apart, it's weak. If it's all over the place, sorry, it's moderate. If it's all over the place, it's going to be called weak. Are we comfortable with those descriptions? Now, if you come across a scatter plot that isn't quite this and isn't quite that, can you imagine a scatter plot that's kind of halfway between these two? Right? You can, if you want to, you can say moderately strong, right? And if it's kind of somewhere between these two extremes, can't we call it moderately weak? So we don't have a lot of vocabulary here, haven't we? Basically get strong, moderately strong, moderate, moderately weak, and weak, right? Would you agree that, you know, it's at least something, right? It's a term that we can use. So if I gave you a description of a scatter plot and I said to you, it was positive, it was strong, and had no outliers. In your mind's eye, wouldn't you be looking at a scatter plot that probably looks something like that? And I don't know, can you actually see what I'm drawing? Right, okay. Because I'm still trying to get into WebAssembly because evidently when I closed a window, I closed out WebAssembly. Okay, it's kicking in now. So we've talked about the strength, we've talked about outliers, we talked about positive and negative. Let's talk now about this situation. Would you agree that, darn it, I need to see what you're saying. Let's kick that picture back in. Right, you've probably been seeing this all the time. Right, would you agree that that is negative and it's strong and there isn't any obvious outliers? Okay, now, would you agree that that is also strong and negative correlation and no obvious outliers, right? Wouldn't it be nice if we could decide between things that look like this and things that look like that, right? Because your scatter plot might. When things look like this, we say that they are linear. You know, linear means straight. And if they're like this, If I take over the world, they will call it this. Wouldn't you call that curved? But that's not what they call it. I do not like this term at all, but you need to know it. Curvilinear, can't even spell it. Curvilinear. Is that not a horrible name for something? I mean, why don't you just call it curve, right? So if it starts with a curvy word, it means it's curved. If it starts with linear, it's linear. Which means we can now introduce that into the vocabulary of how to describe a scatter plot. So how about this one? It's negative, it's moderate, it's curvilinear, I'm not even sure I need the word large, and it is one outlier at 10,30. If I asked you to sketch what kind of scatter plot would look like that, it's negative, it's moderate, it's curvilinear, and I tell you the coordinates of some outliers that it's got. So can we pretend that's 10 and that's 30? Yeah, that's the outlier taken care of, right? 10 is a big X, 30 is a big Y. And then if I do a single kind of curvilinear shape, if you wanted to make it moderate, when I have to make it a little bit fatter. Maybe even a little bit more fatter than that. There, does that look like a moderate, curvilinear, all those things I just said? So we have a vocabulary that we can use to describe scatter plots. Because technically, that's all I would have given you, but wouldn't you write a picture, hopefully something similar to the one I just wrote down here? Question is,
So if you have so there's a convex and a concave side. So if the concave is up, would you call it anything different? Or?
Oh, yeah. If you imagine one that's concave up, wouldn't that be positive?
But then you also have, if it's a positive correlation, you can also have the concave is up. That's convex up, right?
Oh, yeah. Don't use calc terms. I know what you're getting at here. When we're talking about this, just right, curvilinear, right, means it's got a curve to it. And this is considered negative, essentially because isn't it going downhill? And this is going positive. Now, if you got a scatter plot that did a happy face, which I guess you could have, right? Imagine that scatter plot there. That wouldn't fall into any of the categories I've just given. That is not increasing or decreasing. Isn't that doing both? I mean, it's increasing, then later on it's decreasing, right? So that kind of shape there wouldn't be using negative, for instance, in its title. You could probably get moderate. Couldn't you do that bit? You could call it moderate.
Oh, okay.
Or strong
So
or weak.
I was thinking you can have that
right?
as well. Yeah.
Okay. So without going through the dots, you could do that. You could do that. You could do that. And I don't know what on. Right, let's see who they are. You're positive, you're negative, and you're negative. Aren't you just different ways of being negative? Aren't you still going downhill in both cases? Is that what you were thinking of it? Yeah. Both are curvilinear, both are negative. They're just different flavors of it. Right. So I guess I could have drawn a version of that picture that curved more like that. But I think if I did the one that did more like that, wouldn't this outlier be less likely to be an outlier? Okay. Are we, any other, good question. Any others? Again, today is a lot of notes, and that's fine. Notes are good. We're now going to look at what's called a correlation coefficient R. The correlation coefficient R is a number, well, basically it's a decimal for the most part of its life, between -1 and 1 that indicates how close to a straight line the data, your scatter plot is. So the correlation coefficient is a number called little r, and it ranges between 1 and -1. So typically it's a decimal. It's like 0.7, 0.2, -0.998, right? Values like that. And it tells you how close to a straight line you are. So if you got a set of data that was a perfect straight line, like I'm trying to draw here, that guy would have a correlation of 1. +1, right? Positive straight line. If you had a scatter plot whose correlation was -1, it would be a perfect straight line. But do you see the difference is it points down the way, right? Positive means your function is increasing, and negative R value means it's decreasing. So that's kind of helpful, right? So if I had a scatter plot and the correlation coefficient R, I'm just going to call it R from now on, and its R value was 0.7, wouldn't you be able to tell it was pointing up the way? It was positive. Now, if you take an R value, like, oh, I don't know, let's say 0.9, it's not a perfect straight line, but won't it be darn close to being a perfect straight line? So it's pretty strong, right? And if I had an R value, but it was, say, a -0.9, you wouldn't have a perfect going downhill line, but wouldn't you have one that was very strong? So far, so good. Now, what do you think happens if you get an R value that is, say, 0? What do you think a scatter plot for a correlation coefficient of 0 would look like? Perfect straight line? A little bit less of a straight line? What do you think R equals 0 would look like if I did a little picture here? Any suggestions?
Probably like the circle you were describing earlier.
Yeah. It would be essentially, do you know, I've never fired a shotgun, but I've seen things. Do you know if you take a shotgun and you blast it, don't you just get a big circle of nothingness? Would you agree there's no obvious direction or shape to it, right? That's roughly what an R equals 0 looks like, right? So any number from -1 to 1, right, and all the values in between, tell us how close to a perfect straight line you're going to be. So isn't R equals 0, you don't even look like a curve, right? It's even worse than that, isn't it? Just a blob of nothingness. That's a 0. So if you're interested in a kind of, and this is not official, this is just a go-to kind of thing. If you get an R value of 1, it's perfect. And it's a perfect positive straight line. If you get an R value somewhere in the range of about 0.9 to 1, right? So anything that's 0.98, 0.92, 0.9 something, that's very strong. If you get one from 0.9 to about 0.5, then you've got moderate. And if you get a correlation that's essentially anything that's less than a half, you are looking at weak. And the smaller it is, isn't it, the weaker it gets. Right, so a 0.1. So if you had some data and the correlation coefficient was 0.1, and by the way, you will get to calculate this, but thank goodness SALT does it for you, right? You'll be able to put in a scatter plot and it'll say, oh, this guy is R is nothing 0.9 or nothing 0.29, and you'll be able to tell roughly strong, moderate, or weak. Although if you look at the scatter plot, shouldn't you be able to have a kind of guess just looking at it? So these are not hard and fast numbers, but they do. So far, so good. So we can actually use this correlation coefficient to how close to a straight line it is. So let me show you something that you might not have suspected. R is how close you are to being a straight line. Remember that, straight line. Here is a nice curve, a perfect curve. At least I try to make it perfect. You might think, oh, the R value for that is going to be -1, right? It's decreasing and it's a perfect line, but it's not going to be -1. It's probably going to be a number like -0.7. And you might say, but wait a minute, it's a perfect fit. Well, it's a perfect fit for a curve, but it's not a perfect fit for a straight line. And R is only measuring how good to a straight line you are, not how good you are to any other shape, right? So bear that in mind, that although it might look like a really close fit, which it does, that won't work if you're talking about the R value, right? The R value could be quite bad if the curve is very, what a better word, very curved. Can you imagine a curve really very curved? Now, if it was a weaker curve, can you imagine a set of data that was just gentler? And couldn't the R value get a little bit better because it's less curved and more straight, right? So this correlation coefficient is like a number that kind of tells you how good to being a perfect straight line you are. It's kind of interesting. And we call it the correlation coefficient. Now there's another guy that kind of does the same job in a slightly different way. And it's called the coefficient of, I know these are weird terms, the coefficient of determination. Right, the coefficient of determination is a number. It's typically called R squared, mostly because you get it by multiplying R by R. But oh, by the way, when you do correlation coefficients, your answer is will be a decimal unless it's 1, right? When you do the coefficient, let's take this guy. You square this guy and you get 0.49. And then you turn it into a percentage. So the coefficient of determination is a percentage. So it's a number that is a percentage. And it has values that range only from 0 to 100%. Can you see that the coefficient of determination will never be negative because you evaluate it by taking R and squaring it? So if R is negative, don't you get a positive value for your coefficient of determination? So what does this 49% tell you? a lot of what the R value tells you, essentially it's saying this: 49% of the data, and this is the jargon word, is determined by the model. So what we're saying is that 49% of the data is determined by a straight line. So if you have data and it's doing this, right? And you pick your best fitting line that you can think of that goes through the data. Now that I've put that line there, can I adjust it, right? That's your best fitting line. The coefficient of determination is saying, for want of a better word, it's a 49% fit, which means 49% of the data is on that line or damn close to the line to not matter. But doesn't that also mean half the data is reasonably far away from that, right? So if I had a set of data and I told you that R squared was 99%, and I told you that it was positive, wouldn't you be looking at virtually a perfect straight line with maybe a couple of points missing, right? It's a 99% fit. On the other hand, if I told you I had an R squared of 10% and I told you it was positive, can you imagine that's a straight line and 10% of the numbers are on it or darn close to it? But the same thing, wouldn't the other 90% be all over the place? Can you see that that is also a measure of how strong the data is? So a coefficient of determination is just another way of telling you how good your data is to being a straight line. Wouldn't a perfect straight line have an R squared of 100%, right? 100% fit, right? Everybody's on the same line. Any questions about that? So we've got this new number R, correlation coefficient, and another one connected to it, R squared, and they both, in their own way, describe how good a fit you are to a straight line. So now we are going to look at lurking variables, our last set of notes. I'm going to give you some classic examples of what a lurking variable is. Let's suppose along the x-axis, we plot the shoe size of kids. Right, so little children, right? And vertically, we are going to put in the reading age. And you know that there are tests that you can give to children and it will basically tell you the reading age. So if you had a reading age of 7, it would mean that your child is reading at the typical level an average 7-year-old would be at, right? So some children are 5 and our reading age is 10, right? They're exceptional, but they're like that, right? Their reading, their vocabulary is very good. Now, it's not difficult to collect data on shoe sizes and reading age. And let's suppose this is the data that we collected. And if we were using the vocabulary of today that we've learned, wouldn't we be telling you things like it's positive, it's linear, right? What would you think? A moderate for this one? Strong, moderate, moderately strong, somewhere roughly in that line. Okay. So what's this thing called lurking variable about? Unfortunately, when you get a scatter plot and your explanatory variable is shoe size, let's say, and your response is, the reading age of the child. So So that's 4, 5, 6, 7, 8, 9. 10-year-olds, right? That kind of thing. And along here is the shoe size of that child. You will make an assumption that because there's a correlation, that just means there's a good fit to the data, right? Because there's a correlation between shoe size and reading age, that makes shoe size cause the reading age. And this is the fancy sentence that you should engrave in your brain. Correlation does not mean causation. If this was true, that the size of the shoe, you know, the size of your child's feet determined their reading age, right? That's what caused their reading age to be what it is, right? If that was true, just the size of your feet made you read better. If you had a child who had a really low reading age, wouldn't there be an operation where you break their feet and they make them 4 inches longer? And wouldn't they suddenly become much better at reading? If this was true, right? Big feet, you read better. It's not really your shoe size. There is another variable called the lurking variable that is actually why you see this relationship. So if it's nothing to do with the children's directly shoe size that is deciding the reading age, what other variable could be the cause?
Their actual age.
Yes, because would you agree most of the time, older children have bigger feet than younger children, right? A 10-year-old's going to have most of the time, right, on average, bigger feet than a 4-year-old. And so we would call the lurking variable the age of the child. In fact, if you wanted to test that, couldn't you just go back to the data and find out what the ages of these kids were and change this to age of child, reading age? And shouldn't that work out that a 5-year-old should read like a 5-year-old on average, and a 10-year-old should be the reading age of a 10-year-old? And that is what we mean by a lurking variable. It's a hidden variable, right? It's lurking there, sometimes in plain sight, which is actually the real reason you can see the relationship, the real cause of this one. Here's another story. It's also going to have a lurking variable in it. The explanatory variable this time is going to be the number of cars that a household has, right? So 0, 1, 2, 3, and 4, I guess. And the vertical one is going to be life expectancy. Which basically, how long does the average person in these countries live? So I've collected data, right, on Japan. What's the average number of cars they have in a household in Japan? What's their age, right? What's the average age that they live to, right? And if you do that, you will see the following. So you might be down here at 60, 70, 80, and you will see data that is pretty linear and pretty close. Right, so each one of these dots is meant to be some country in the world, right? And you might have a weird outlier or two. Let's pretend they're not there for argument's sake. According to this then, the number of cars that you own makes you live longer, right? More cars, you live longer. Does owning cars, is that the cause of living longer? No. I mean, if that was the case, wouldn't people just buy lots of cars so they would live long? Right? So what is the lurking variable this time? Why do countries that have lots of cars live longer than countries where they don't have a lot of cars in general?
Probably like better healthcare or something.
Yeah.
Is there? Well,
Yeah. Right. Let's work on that because you're in the right ballpark area. What?
Because they live longer, they can
Yeah.
purchase cars at older age.
No, don't go there. I like the health one that Zach's on. I'm just going to tweak it a little bit. If a country has really good healthcare, what else has that country typically got? A lot of money. Isn't the looking variable here really the wealth, which we normally use a number called the GDP, right? Which is gross domestic product. The wealth of the country is the real reason. Would you agree that countries that are really rich will probably have a lot more cars per household than countries that are really poor? And countries that are really rich also have better healthcare, better food, better housing, better security, right? You know, you're not going to get robbed and shot. You know, in some countries in the world, you know, life is dangerous as well as unhealthy, right? So all of these things tend to work better in rich countries, right? You have more of everything, and more of those things tend to make you live longer. So if you are looking at a scatter plot and you see a really good correlation, right? A really good, nice straight line, do not fall into the trap of this thing is causing that thing. Right? Could it be true? Yeah. In some circumstances, won't this variable actually be the main cause of that one, right? So the explanatory variable is a good reason for the other one, right? But it isn't necessarily the case. And so be aware that some people will tell you things that are, strictly speaking, not correct, even although they're going to baffle you with science and says, it must be correct. Look, a correlation coefficient of 0.9, that's almost a perfect straight line. And that means that this is causing that. That is not the case, right? These don't show that information. Let's try one last one. Let's pick something like, what shall I pick? The number of hours of TV you watch in a week. Oops, in a week. So we got 0, 5 hours, 10 hours, 15 hours, 20 hours. And here, for the same person, we found their weight, or their average weight. So we collected a lot of people who watch 5 hours of TV a week, and we found their average weight, right? Or whatever. Or it could be single people, I guess. And this is the pattern that we got. And I'm making this positive. Chuck in some outliers. There's your data. Right, if you were describing this data, would you say linear, positive, maybe moderate, something like that? But this is the question I'm interested in. The number of hours of television that you watch if you compare it against the weight of the people who do that, would you agree that the more TVs you watch, the more hours of TV you watch, the heavier that person tends to be? Now, do you
Yes.
think would you say that watching TV is making you fat? Is that the cause of you being fat? Because I'm saying that there's a lurking variable that's the real reason. And TV is just a reflection of that same reason. What on earth could be a different reason for why this pattern is visible?
If they're willing to sit that long watching TV, then they probably have a sedentary lifestyle that affects their weight.
Yeah. So isn't the number of hours of TV just a number that's reflecting their lifestyle, i.e. I'm a couch potato, right? And does that mean there's people who watch 20 hours of TV and are marathon runners? I'm sure there is. But in general, would you agree that the more TV that you watch, the more sedentary, as you said, Zach, is your lifestyle? And would you agree that sedentary lifestyle then has other issues? Don't you probably eat too much while you're watching TV? You don't exercise so much, so you don't lose the weight that you might have if you were active and ate a lot. You know, those kinds of things. So what we're looking at here is a lurking variable that is basically, I'm just going to call it lifestyle. Isn't it a reflection of I'm a couch potato lifestyle rather than I'm a, less TV might be an indication that you're doing other things that are healthier. It's not guaranteed. That's why I've gave you some outliers. Right. I mean, look at that outlier. Doesn't that person watch lots of TV, but it's actually quite light? Right. Isn't that person doesn't watch a lot of TV and is really heavy? Right. So there are always going to be exceptions to any general pattern, but we focus typically on what the major pattern is. In fact, let's rewind that story a bit silly. Your doctor doesn't weigh you when you come into the office anymore. He just says, how many hours of TV do you watch a week? Now, if he did that, wouldn't that be a rather weird way of figuring out what the average weight of someone is? That'd be a bit silly, I would say, a little bit silly to do that. And for our last thing today, we are going to do what politicians like to do. And we have a name for this. It's called extrapolation. Extrapolation is when you collect data, you normally collect it in a certain range, right? So this is what your scatter plot would look like, right? So you collect numbers and they started at, well, let's suppose we start at 0. Right? So they started at 0, 5, 10, 15. Let's say you only collected data on up to 20, right? And vertical number in this case is going to be, what shall we do? For the vertical, we'll do your age. And what I'm talking about here is age that you live, right? Your life expectancy. And so along here is going to be the number of minutes per day that you go walking. And this is about 80, and this goes up to, let's say, 81, 82, 83, right? So we're looking at a group of people that we collected data over their lifetime. That person that has a little dot there, they did 5 minutes a day exercise, walking, and they lived to a little bit over 80. This person did 20 minutes per day, and they lived to about 83, right? So far, so good. Now, extrapolation is when you go and you do this. Well, you can find a straight line that fits the data. None wrong with that. And couldn't I use it to predict then? If you do 15 minutes a day, you're probably going to live to you're about 82. Nothing wrong with that. That's a predictor. Now, this is extrapolation. And you go way over here, and let's make that 300 minutes. In other words, 5 hours of the day. And this number up here is 100. According to this data, if you continue that straight line forever, somebody who did 5 hours of exercise a day would live on average to 100. That's called extrapolation. And you remember our data stopped here. So our data is only good at predicting 0 to 20 minutes a day exercise, right? Because if this was true, couldn't you just continue and be silly and say, oh, well, if you do 12 hours of exercise a day, you'll live to your 200. Do you see that you end up with a point that is no longer in reality, right? So how do politicians do that? Well, they collect data over 2 or 3 years, right? And they'll say something like, if this continues, 40% of America will be unemployed, you know, by the year 2030. Yeah, that kind of predicting into the future. So do not predict into the future, because couldn't this basically just level off? Couldn't it just basically be the data kind of does that and nothing really happens after a while? In fact, it might actually do this. Because if you do 5 hours exercise a day, couldn't you actually hurt your body because you're doing too much exercise? Right. Let's do another one like that to show you the dangers of extrapolation. So these are babies. There's 5-year-olds, there's 10-year-olds, there's 15-year-olds, and there's 20-year-olds. And this is their height. And you wouldn't be surprised, agreed, that the data is not great, but it is positive, right? Linear, positive. Right. A few more dots down here. There we go. Now, if I wanted to use this data, couldn't I say, okay, there's a 16-year-old. A 16-year-old on average is probably going to be that height, right? That would be one way that you could use it. In fact, Leanna, you'll back me up on this because I know you've got a kid. When you go in and get your kids' checkup, don't they get your kid's age and they have a little chart that says, yep, your child is weighing this. This is a typical weight age for a 2-year-old girl. This is a typical height for a 2-year-old girl, and all the other typical things for a 2-year-old, right?
Yeah, and then they compare it to a curve.
Well, okay, so it's curvilinear rather than linear,
Yeah.
right?
But it's
Okay.
like the same thing. Like they want to make sure that they're following along on the
Right.
typical, like all these kids are usually here. Where does your kid measure up to all these other kids?
Now, if you use this data, and I've got it linear because I'm predicting it, if I did extrapolation then, couldn't I find out what the height of a 50-year-old is? And wouldn't the height of a 50-year-old be something like 10 feet tall? Because extrapolation assumes that the data just keeps on doing what it's been doing before. But we know, don't you basically flatline after about 18 or 20? You know, that's as big as you're going to get. So do you see that if you stop at 20, but then you use it to predict beyond 20, isn't your prediction going to be totally wrong, right? Extrapolation means projecting from the given data into the future, right? Into a bigger place that you've never collected data. And that's always a danger, because who's to say that straight lines continue to be straight lines, right? Couldn't they just level off, as, for instance, height would do? Would you agree that would also be a danger if you were using it to forecast? Because that's another thing for extrapolation. If you were using it to forecast the temperature in the future. Suppose these are representing the last 100 years and this is the average temperature. you could be predicting it into the future doing that. But couldn't the temperature be cyclic? In which case, predicting into the future is a very dangerous thing.